Hi, in this chapter, we're going to look at scatterplots, association, and correlation. So if you look at the graph on the left here, what we have is a relationship between two quantitative variables. So you could see that my x-axis is the height and my y-axis is the weight. So these are my two quantitative variables. You could see that the dots on the graph, those represent the heights and weights of certain individuals. So individuals are represented by dots on the plot. Then we have the explanatory variable, which is x. So one way to remember it is explanatory. That is our independent variable on the x-axis. And we have the response variable, which is our dependent variable, and that is our y-axis. So that is what we want to predict. So for example, if you're a height of 72 inches, what weight should you be? Now, again, this does not mean because you're a height of 72, you will be this weight. And that's something I'm going to talk about later on when we talk about association. All right, so let's go ahead and continue. All right, how do we interpret a scatter plot? When we're looking at a scatter plot, there's an acronym, there is, oops. I didn't mean to do that.
I'm not sure I understand.
Yeah, I don't either. How did that happen? All right, the next thing we want to look at when we look at scatter plots is how we interpret scatter plots. So just like in the beginning chapters, we learn how to interpret distribution using the acronym SOX by shape, outlier, center, spread, and of course always context. We're going to do the same thing for scatter plots. We are going to describe a scatter plot always first by the form, if there are any outliers, the direction, and the strength. So let me talk about each one of those, what they mean. So the form is either going to be linear or nonlinear. Now, if you prefer to use the word curved, you could say curved. So for example, when we're looking at the first scatter plot here, the pattern appears to be somewhat linear. Now, they're never going to be perfectly linear, but we're going to have a scatter plot that it's going to be somewhat linear. So let's look at the top one here. Even though this is not some line, we would say that this is a linear form of height versus weight. Now let's go ahead and take a look at the form. So it's either going to be linear or nonlinear. The next thing we want to look at is if there are any possible outliers. So it doesn't mean there will be an outlier, but we want to look for a possible outlier. Now, possible outlier, for example, on this curve, if I have the data following a certain pattern, I could have maybe one outlier somewhere out over here. So this would be considered a possible outlier. The next thing we would want to look at when we're describing a scatter plot is the direction. So you could see for the direction, it's either going to be a negative direction or a positive direction. So just like when we're looking at a regular line in algebra, we can tell by the slope or by the direction. We always read from left to right. So if I'm over here on the left, you could see that the direction is negative for this scatter plot, whereas from over here on the left to right, reading it, I'm going up, so the direction is positive. So again, direction is either negative or positive. And what we say is if two quantitative variables have a negative direction, we say it is a negative association. And if it's a positive direction, we say there is a positive association. The next thing we want to look at when we're looking at a scatter plot is the strength. We want to see how strong the data fits. So what you want to imagine is if you're looking at a scatter plot, so the words that we use for strength is either strong, moderate, or weak. Now, of course, you could have something in between moderate and strong, so you can use the words moderately strong, and you can have something that's not quite moderate but not weak. You could say moderately weak. So any of these combinations are how we would describe the strength of a scatter plot. So let's take a look at the first one. This one would be considered strong. And the second one here would be considered somewhat moderate. And the one here on the left, on the bottom, is weak. And this one here that says scattered basically has no association. So you can't really tell if the graph is going positively or negatively associated. There is absolutely no direction. There's a scatter. So you would say there is no association. Now, one trick you could do to tell if data is strong or weak is to draw a circle around your data. So for example, if I drew, I should say an ellipse, not a circle, but if I draw some type of ellipse around here, the narrower it is, the stronger it is. And obviously we could see this is going from left to right in a positive direction. Now you could see that this is a little bit weaker because my ellipse is a little bit wider, is not as steep. So this is weaker than the above scatter plot. Now, weakness or strength does not really depend on direction. So you can have something that's strong that's negative. So for example, this is going down. If I drew some type of ellipse around here, this would look like it is somewhat moderate because you could see that the closer the points are together, the stronger they are. And on the bottom one, where there is no association, you could see when I'm drawing, I have a circle. So when your data is somewhat of a circle, then it is scattered and you will have no association. So we're going to be looking at examples. So far what I have mentioned is you want to describe data with directions that's either negative or positive. You want to mention if there are any outliers. You want to talk about the form, which is either linear or nonlinear, and then you want to talk about the strength. So the acronym you can use is DOFS, D-O-F-S, to remember. All right, I'm going to do a few examples how we could describe a scatter plot. Of course, there's no x-axis and y-axis, and you'll always have an x and y-axis labeled with your points. So in this case, if we look at the graph, this was my y-axis and this is my x-axis. So if we can look at this, we could see that there is some type of cluster here. Then the graph goes positively, but then it curves and then goes positive again. So we could say that this is a strong curve positive with a cluster at wherever the cluster would be. So you can say a cluster between, I don't know, let's say this was 10 and this was 15. You could say there is a cluster between 10 and 15. But this is definitely curved data, so you could see it's nonlinear. Number 2 definitely looks like it is strong. See if I drew my little ellipse around it. It is strong. It is going in a negative direction and it is linear with no apparent outliers. Number 3 looks like it's pretty strong, although it's not as strong as number 2. So we can say it's moderately strong. and it is also positive. It's going up. And there appears to be an outlier right here. Now, usually if you see an outlier on a scatter plot, you would say where that outlier is. So in this case, I'm just calling it XY. It is an ordered pair. I don't have a scale and no X and Y axis here, but if I did, we would say exactly where that would be. All right, so the next thing I want to talk about is something that is introduced in this chapter, which is called the correlation coefficient. And an example I could show you with that is, how do you determine how strong a relationship is? So for example, look at the scatter plot in A versus the scatter plot in B. If I asked you which one was stronger, would you be able to tell me which one is stronger? And if you said you couldn't really tell, then you're probably right, because both look just as strong. So how can we determine which one is the stronger correlation? Well, we have something called the correlation coefficient, and that is given by the symbol R right here. And it is a number, and the number is always going to be between +1 and -1. So what does that mean? It means the closer you are to either -1 or +1 means a very strong correlation, and the closer you are to 0 means you are very weak. Let's look at the formula, which I don't expect you to memorize, but the correlation coefficient is given by a formula. And that formula is actually made up of, if you recognize this, you have an observation minus the mean over standard deviation. Do you remember what that was? If you said a z-score, you're right. So actually a correlation coefficient is the sum of the z-scores of x times the z-scores of y over n minus 1. And your calculator will give you an R value anytime you input a list for X and Y. So let's talk a little bit about this formula and see what that means. So first of all, as I mentioned before, correlation coefficient is always between a number between -1 and 1. The closer to -1 or +1, the stronger the relationship is. If R is positive, in other words, R is 0.8, 0.7, you have a positive correlation. If R is negative, then you have a negative correlation. If R is equal to 1 or -1, then you have a perfectly straight line, which seldom happens in real life. Correlation is the same no matter which variable you use. So for example, if you decide your x-axis and y-axis, if you switch them around, your correlation will still stay the same. So that's what it mentions here. Correlation is the same even if you change the units. So for example, if I wanted to, for the graph above, have the heights versus the weights, and my height was, let's say, in inches, and my weight was in kilograms. If I change that somehow to pounds and feet, then the R would still stay the same if we're looking at the same data. Now, correlation is non-resistant to outliers. So if you remember what else is non-resistant to outliers, that would be the mean. Now, why is correlation non-resistant? Well, if you look at the formula, we are actually using the z-score, which tells you how far you are away from the mean. So if the mean is non-resistant to outliers, that means a correlation coefficient will also be non-resistant to outliers, which means if you have an outlier, it will change the correlation coefficient. All right, the last thing I want to talk about, which is extremely important, is correlation does not imply causation. What does that mean? It means that, for example, just because two variables are associated, it does not mean that one causes the other. So if you saw in the top example with weights versus heights, this would be a good example. Just because you have a height of 68 inches, let's say, it does not mean that you should weigh a certain weight. So there is an association, but it doesn't imply causation.